Okay, good morning, everybody, and welcome in this Friday, 13th to lecture 18th, in which we have one of our favorites, the MEP systems. We'll try to do it in 2 sessions. I forgot the microphone. Now it sounds better. Okay, so today we will try to see artificial lighting and mechanical systems. And next week, we'll see all the rest, including fire protection. So we can go straight into integration and sustainability, and then the review lectures. Just a reminder, I will not repeat, but as many people miss it, remember next week we have to submit envelope systems, and this is the guidelines. Right. So the plan, as we said, is to the artificial light and mechanical systems, and next week we will see, hopefully in one session, plumbing, electrical, conveyance, and safety. The photo is Intercontinental Hotel in Quex. This is the roof, which you see almost the full roof is packed with machines. And intelligently, the ventilators, all the climatizing machines, which are very noisy, are in a kind of pit, so the sound doesn't go horizontally, doesn't disturb the neighbors. Let's start with artificial light, with a famous old photo of the Guggenheim Museum in New York. Frank Lloyd Wright was very much conscious on how his buildings would look at night. That's the period of the golden age of artificial lighting, right? Just right after the Second World War, 1945, artificial light became the standard in buildings. As we did with sound, let's go to the basics of light. I will spend a bit more time in this part because I think we don't study so much at school. Mechanical, also the extension is the same. Since all you took all the environmental systems course, maybe you are already quite familiar with it. So just a revision, color is part of or visible light, right? Is part of the full vibration spectrum. So what we can see is just a tiny part of that vibrational spectrum, those waves, right? And we can see between around 400 nanometers, that's very, very short wave, to around 700 nanometers, which is wider wave, right? This is like a infrared beyond that, or ultraviolet on the left. So this is an interesting graph, which lets us compare how light distributes those different waves. And sunlight is the reference. It's not perfectly regular, but it is very much weighted to the center, right? Between blue and yellow, red is a small part of it, and the brilliant white is, or blue is another part of it. So this is how our vision has been created and evaluated. It is fine-tuned to this kind of distribution. The same as we say it with sound, we are more sensitive to some areas and we balance the sound depending on the different frequencies. The same happens with light. Only with light, probably we are more conscious because we can see and we are very much a visual culture. So if you see the incandescent, or this is a halogen light, which has been the standard before we had LED. It is very similar curve, only shifted a little bit towards red. This is why halogen looks a little bit yellowish compared to daylight, right? But it is very pleasant light because the distribution of the waves is very much similar to the one of the sunshine, only a little bit shift. So colors change a little bit, but feel very natural. It's kind of pleasant light. In the other side, the worst is the mercury. Mercury vapor are the street lights, right? Street lights need the intensity, but color rendering is not a priority. So you see they have spikes at some points. So the spectrum is very incomplete. They have samples of almost everywhere, very much shifted towards the blue. This is why the street lights are so cool, so cold. Mercury is like a bluish, but you will never have a pleasant sensation, and colors are never so precise. Here we don't have sunlight, but we can have a halogen as a reference. I will change the color, right? So halogen, say it. Incandescent light is very similar, a little bit more shifted towards the red, right? This is why, again, incandescent light is quite pleasant. And also most countries are banning it because of energy. It provides a very good quality light. And if you work long hours under incandescent or halogen light, your eyes will be less fatigued, less tired than working with a fluorescent or LED or other kind of lights. That's something which we didn't solve. Other thing, so to note, if you see the spectrum, there's a lot of that spectrum we cannot see really. It becomes just heat. And this is why they waste energy and we try to use less, right? So we have kind of conflict there. Saving energy versus the quality of light. And this is something we didn't solve yet. We are doing a more efficient lighting, but less healthy and less pleasant to our senses. This is the LED, and LED is evolving, it's getting better. Let's concentrate on the visible light. So what makes LED so efficient, there is almost no heat emission, as we know. But you see the graph is very natural. It's kind of balanced. You have all the colors, but in general, it's quite much shifted to the blue, right? It is corrected. They have filters and things to shift a bit more natural light, but the spectrum it gives is very unnatural. So probably it's among the worst quality of light we have. Just a moment, I think I missed one thing. The fluorescent light, which is the second best, right, has many peaks, as we saw, but differently than the mercury vapor we saw before. In general, it follows very much the natural light. Right? It has many peaks. Very good quality fluorescents are calibrated to fill a bit the gaps. So some of the best quality light we have nowadays is also fluorescent. Right. You will see in commercial catalogs LED with very good quality lights and very good rendering. That's mostly marketing. Very good quality LED, to have it, you need to use a lot of LEDs and calibrate it to have the full spectrum. I brought just a case study, an example. You know, artworks are very delicate against lights. The problem with halogen, which has been the standard for years in the museums, they have too much infrared energy that deteriorates the painting. LED doesn't have that problem. So Louvre tried to have artificial lighting of better quality for the famous Gioconda. So they fixed it with the LED, but the problem was the color rendition. How did they overcome that? So it was Toshiba who was in charge of that. There's full articles on the whole process. You have the link if you want there. But the point is they needed to make a compound of 34 different lamps to complete the spectrum. And they spend time like calibrating the color, so you have the perfect white for that painting. We have to assume that Gioconda was painted with the daylight, with sunlight. Sunlight nowadays changed a little bit, but it's mostly the same as it was 400-500 years ago. Right? So that's only to let you know that you can have very good quality light with LED, but it comes at a cost. Right? Don't believe those cheap LED which have very good quality color rendering. So there are two basic qualities in light we have to deal with. One is the feeling of light, colder or warmer, and then color rendering, right? How much precisely they render the color. So we measure that with a color temperature and then color rendering index. Color temperature, when we had just a fluorescent and incandescent, was very easy. But now we have a full spectrum of LED and then can calibrate the colors. We have to be careful with that choice. So in that table, let's go back one moment. The standard, right, is like the daylight, which is very high temperature. The counterintuitive thing is that high temperature is blue, low temperature is red. Looks the opposite, but usually incandescent bodies, the hottest, they come the whitest, the light. Well, those who are in astronomy know very well, because this is how we know the state of different stars, bodies in the universe. So the fluorescent light is still on the middle area, but see how the quartz lights, right? And we don't have tungsten is the incandescent light, have always a shift towards the red. So you will have like probably 3000 K for a warm, lovely interior, but you will try to go to 4, 5, 6,000 to mimic daylight. So these typical values. So 5 to 6,000 is the one we try to use in public spaces, offices, classrooms, and so on, right? While in houses, restaurants, places to be relaxed, we go to somewhat warmer light. We know also that warm light doesn't disturb our hormone production of melatonin, so it is easier to sleep at night, and so on, right? And 10,000 is just the daylight, the real daylight. We seldom do it with artificial light. The same as it happened with the sound, right? The cooler colors, the higher temperature, have the impression of being more intense, even though the intensity is the same. Color rendering index is a bit more subjective. It's difficult to calibrate. Well, you can measure it, but actually our brain is so good in recomposing colors that we're not so much conscious of that loss of quality. The standard is to have like a 70 to 80% color rendering index. This is the precision which is the light lets us know the colors. Around 70% or 80%, we will not realize that it changes, right? And this is the general lighting we use. 90% is like, or more, is the one we'll use in museums, exhibitions, markets, if you want to see the color of the vegetables or the fish and things like that, right? This is an interesting table. It's a bit small, but in the handout you will see it with precision. You will see that the poorest is the street light. The sodium light is the orange light, right, which makes almost all of us colorblind. Mercury is a bit better. You have better quality mercury, which was really astonishing, 60%. the area we want to be in general is like between 80 and 90, right? And you will see that in the 100, we have incandescent, halogen, and very good quality fluorescent. LED, well, maybe we have some brand around there. I don't know exactly because there's many brands, but LED is not in the top league, right? You have to be really expensive and really specific lamps for that. When I visited the restoration area in Prado Museum, all the experts had like a very good quality fluorescent light because of the heat problem. Right? This is quite unique view. This is one Lemian apartment complex, and you will seldom see all the lights lit with the same color. This is very unique of Korea. They provide apartments already with the light fixtures and everything prepared, so you don't have choice. So they just check electrical power and the functioning of all the systems before finishing the construction, right? So it was just a coincidence, I could say it, very unique image. The most common is like this, right? So everybody have their own preferences or has their own preferences. So you can see the wide range of light color. Once you're in the house, you don't notice, but that really changes the perception of the space. Right? In Korea, still, same as in Japan, fluorescent is very much the standard. And now we have LED, but in most of Europe, we will go towards this kind of warmer light. We will feel this kind of white light is kind of office, school. We don't feel like homely light. Let's go into intensity. And here we are again with very basic mathematics, but we have to make some numbers. It is very simple things. The formulas we see here is just for you to understand the concept and to make very fast checks if you want to do for your project. Usually we'll use software, right, as we do with sound. So intensity, we have several parameters. I, which is the light intensity of the source, right? Light bulb, the fluorescent tube. This is usually measured in candela or lumen. Lumen is the most common you will see in catalogs, right? And the rate between candela and lumen is 4p. You know that 4p is very much related to the sphere and that distribution. But if you want to, if you have the data in candela or lumen, you can make the conversion. But the most common is lumen, right? That is the light which emanates from the lamp. So you have one bulb. From the light bulb itself, we have X lumen of light, right? More light is more lumen, right? And even more light is even more lumen. But this is from the emission point. The second is kind of the target. The level of illumination we need in one space. In one classroom would be the light on the whiteboard. In the library would be the light over the desk, right? Usually desk point is the standard, right? But in displays, you have to set distance to the displayed object. And the unit is lux, which is 1 lumen per square meter, right? So if you have this kind of light coming here, we have the area 1 square meter, right? And we calculate how many lumen coming here. We divide by the area, and we have the intensity of lux, right? If well, that's the point. We'll see how we calculate. 1 lux is approximately the light of full moonlight. So 1 lux is something, if our vision is not impaired, we can see quite well, but we are missing a lot of detail. And well, this is the conversion to the British system with food and so on, if you want to use it. One more parameter, which is interesting, is the efficiency, right? LPW, which is the ratio between lumen and watt of a lamp. So the illuminance or the intensity it produces related to the power they need to produce that light. So let's have a small exercise all together. We have a commercial light, right? We know it is 21 watts and has 2700 lumen. This is I, right? It has an angle which is 51 degrees. So we want to have 500 lux for kind of commercial display. So we want to know first, there are two questions, but actually we have to reply first to the second one, right? How much area will the 2700 lumen lamp lit with the 500 lux, right? So we have to know the area. So we know, let me see if we have one more thing. I have it, but we already said that illuminance is I divided by area. So this is quite fast, right? I thought, yeah, it is put here. So the first question is very fast. Can anybody make the numbers? So the area is I divided by A, right? Is 2700 divided by 500. And that is how much? Come on, you can go so far. Can anybody make the numbers? Mentally, yeah, it's easier. It's like 5 point somewhat, bit less than 6. 5.5 more or less, 5.4, right? So with that area, we can calculate the radius, right? We know that area is PR to the square. So R, the square root of A divided by P. Am I right? Yes. Can anybody make the calculation? 5.4 divided by P. It's a bit less than 2, right? 1.7, 1.8. What's the mental calculation power? Did anybody calculate the radius? Please. 1.3. So my mind calculation was quite far away. So 1.3. So the diameter is 2.6, right? So we know that if we put the lights like 2.6 meters away, we have quite regular light, or we might join them a little bit more if we want to have overlapping node gaps, right? In this case, they put them with the gaps to have a bit variation of light. The distance, we know this is a 26, half of 51, right? We know the radius. So we know the tangent is radius divided by d. With that, we make the change. The tangent of 26 is approximately 0.5, 0.48, right? With that, we see the distance we have to put the lights to have this kind of illuminance, right? Which will be like nearly 2.7 meters, 2.6, right? So the data were done just to have the same distance between lamps and from the lamps to the object, right? So this Yeah, suddenly the message that I'm recording came now, but we are recording since the beginning. Okay, so this is very simple calculation. And once you have the data from the maker, you can plan more or less your display, right? Of course, you will have some specialists, something like that, but for small projects, you can do yourself and have an idea on how many lamps you will need and how you have to make the layout. So these are some examples of light intensity we can find in nature. As we said, the one lux is full moon, right? 10 to the -4 is the really, really dark night, but still our eyes can have some kind of vision there, right? And the most common intensities we use in interior design are between 50 to 500. Right? 3 to 500 is the working space. 100 lux is just a general use, like rooms and so on, right? And 550, unless it's like really the basic lighting to have some pleasant light, but not enough for reading or doing some kind of work, but still pleasant to see around. This is some basic standard for rooms. There's a lot of margin, right? Because lighting is very subjective and depends very much on individual ability. But as we say, for example, for corridors, 150 lux is quite brilliant. So people with a disability can still see their way very well, right? And education classrooms, the average is like a 500. So you have the 500 like average for intense light in a working space is quite okay, right? In surgery rooms, you may have almost daylight, right? Minimum is 1000. And at the street, that's the night orientation. You won't see details, but you will find a path. We aim at least 10 lux, right? Of course, we have standards and depends on the countries and the cities depending. So we saw for one lamp, when we have several lamps to lit one full room, the principle is the same, but we have a basic formula just to have a pre-dimensioning. Then always the engineer, the specialist, or the light company will complete the calculation for you, but have some idea, right? So we already are familiar, the required luminance. Let's say it's like a 500 lux, for example, as in the classroom. The room area and the height in meters, we are using international system, always meters. Then the luminaire is different than the lamp, right? Here we have luminaires which have, well, they changed. I see 2 lamps each, right? They used to have 4 lamps, professional lamps. So this is the number of lamps you have, because the data we have from the maker is the intensity from each lamp. So the I is per lamp. So we have to multiply I by the number of lamps to have the intensity from the luminaire. And then the watt power, as we said, to understand the power intensity or the power density of the installation. We have some coefficients to reduce, because that's ideal data. The coefficient of utilization is very much a rough estimation, right? And depends on many things. Usually the maker make the correction for the specific luminary, right? So you have not only the lamp, they have mirrors, they have filters, they have diffusers, and the maker has the experiments and they tell you the coefficient you will use to have an approximate real amount of light. Light loss factor is also some estimation. Lamps lose intensity with time, they become dirty, and so on, right? And we just make a very rough estimation about 0.7, right? Often in this utilization, they give some kind of coefficient for the distance from the luminary to the workspace, which is about 2 meters in general, something like that. So the formula is very plain. It's very long, but we need the lumen, we multiply by the area because we need to know how many lamps we need, right, in general. And then we divide by the coefficients, right, which reduce the power, the number of luminaries, and the intensity of each. It's very plain formula. And the power density is just the multiplication of the luminaries by the weight divided by the area. So we know how many watts per square meter that installation costs. It's very simple, plain mathematics. Let's make one example with these two formula. Go to the question 2. We have the formula here, so you don't need to memorize. We have a room of 100 square meters, which is probably a bit smaller than this, right? But we might be around a bit more. We need the 500 lux, which is kind of a standard for working space. We have luminaires with 4 fluorescents with a 2850 lumen, 2850 lumen each, which is quite a standard from the industry, right? And we already have the watts per luminary. So this is for the 4 lamps. We don't need to multiply. 111 watts, which is also quite realistic. The CU, this is the maker. So we consider the ceiling is 3 meters high. So it's 0.7, which is quite the standard. And we use the utilization 0.7 also. So we don't need to worry about it. So we need to know with this data how many luminaries we need and the power density. There's the 2 data we usually calculate, right? Anybody makes the numbers for me? So just put 500, 100 up, and then down we have 0.7, 0.7, which is roughly with 0.5, N, which is 4, L, which is, or I, sorry, which is a 2850, right? So you have all the data, and that gives the number of luminaries. Anybody makes the number for me? Cannot hear. 8. Okay, let's say 9 about, right? Which is quite standard. That means about 1 per 10 square meters. This very, we can say 1 between 10 to 15 square meters. It's quite reasonable. That gives a very regular distribution of light, right? And in this class, we have the main ones. We have 8, right? So probably they're powerful, but that gives enough light if we consider those artificial light. So with this, we have an estimation of how many we need. Then we decide, because it depends on the proportion of the room, the layout, we may put more or less, but we already know the number. And the density is very so. Suppose we put 9 luminaries, multiplied by the power, so it's 999 divided by 100, which makes about 10 watts per square meter, which is quite standard for office space and classrooms and so on. So you have a big building, you can just estimate how much power is used only for lighting. And then you decide you'll put better windows to use less electricity. Okay, so this is a very fast, simple calculation. Let's continue. I think that was the most difficult question today. There are more things to consider. So the glare, right? The electromagnetic compatibility, dimmability, and some issues. Let's go fast into them. First is glare. Now we have a cloudy day, we have shades, we're projecting, so the light is very soft, maybe a little bit insufficient. We may be in the 100 lux in the ballpark, right? Those 10, for example, maybe over 500 lux. Like the brightest city is now here. Yeah, just shining today. If the contrast is very strong, we have the glare, right? And that is standardized and measured. And this is something which we have to consider in the design. So there is the unified glare rating, and luminaries have this rating, right? It's an index which makes how much discomfort you may have with a light source, a luminary. And it is between 10 and 40. 40 means it's really unpleasant, very aggressive to the eyes. And 5 is like we have today, ideal. We have not any kind of too much contrast, no much disturbance, right? So in general, for luminaries, around 10 or less is quite acceptable. We have quite pleasant space and we don't have aggression to our eyes. Over 30 is almost unbearable, right? You will feel really uncomfortable. This is from the British standards. It's not easy to find data, but we have here some kind of the requirements for glare in different kind of spaces. Electromagnetic compatibility is something we commented very fast with the acoustics. That happens with the electromagnetic light, right? So basically is the problem of fluorescent and the LED. Incandescent light and the halogen works by incandescency, by high temperatures, the same as the stars and the sunshine. This is why they have so much pleasant light. But these are electronically generated. They have their vibrational by system. And that is a vibration we have in the lamps and in the ballast. They have some accessories which may create interference with the radio, television, internet, and our own hearing noise, right? So that's maybe a problem, and that is regulated by each country. Almost all lights and devices will have a seal, a certificate of compliance, which often is faked. So careful when you buy knockoffs and cheap things in the markets, because they may be not compliant with those things. And we commented the other day that fluorescent has been in the market for over 80 years. So it has been calibrated, and fluorescent lights are very reliable. LED, even though we have been long time using them, still quite novel. And still, that I know we don't have them right. This is an example of actually Philips, right, which is not cheap knockoffs, right? And this is the most strict electromagnetic emission limitation. This is more loose, and we see that those very expensive, very posh lamps exceed many of those radiation points. That can be corrected, but you need somebody who knows, right? Things are improving, the industry is working at it, but we have the cases a few years ago of full office towers, like hundreds of thousands of square meters, changed with LED, and suddenly all the electronics totally going wrong, dumped because of that interference. And that the cost of fixing that was way over the savings in electricity. So the industry is improving. I didn't check this for 3 or 4 years, but just be aware of that, right? When you plan to have a huge LED use. The other point is the mobility. The same as sound, right? With sound, we can change the volume very easily, but most of the lights we use is like a on, off, all or nothing. Also in this class, we can just turn areas, but it's always the same intensity. In the same lamp, to change the intensity, we call it to dim. This is done with a dimmer. And not all lamps can be dimmable. So this is one of the factors you can check for the lamps you use, right? The basics is a phase dimmer, like an old-fashioned changing the electricity intensity, and when you have less power, you have less light. Right? It was very easy with incandescent light or halogen. You have less intensity, it has less power, and you have less light. But we have, especially with LED, not only LED, but mostly LED, intelligent electronic controls. And this is in development. Interesting, however, and there are two standards, DALI and Casambi. They can be controlled. Casambi is one maker. DALI is more open protocol. And then you can have apps, Bluetooth connection, and many ways of controlling light, which will not go into the details, right? But will be another thing which is interesting. LED lamps have so little power that sometimes even with the power off, the lamp still lit, right? When you have very few lamps. Why is that? Because the general electrical system, even if you close the switch, those networks are so complex with the grounding, the connections, and so on. There's still some electricity moving around. Very little, it's not dangerous, but electricity is never out, right? So that small electricity is enough to lit the bulb. Then it absorbs the whole electricity and turns down. Then electricity accumulates and turns on. You have like a LED just blinking when you have the light off. It's very annoying. How you can do it? With more strict electricity installation and switches, which is not an easy option, or increasing the power, or adding more lamps in the same circuit, which also may hinder your savings. Right? The other thing which happens with the fluorescent is the reactive power. This is why they need some kind of condensator and so on. The electricians and the electrical engineers know well, so they have devices to absorb that, right? So you don't have more power expenditure than necessary. And we have the vibration and the harmonics, as we said before. So this is the last activity. This is very easy. This is a commercial catalog of very good quality lamps. So they give you all the technical data. Now you should be familiar with most of them, so you know what you are choosing about, right? Let me just point, for example, you have a range of color temperature, right? From very warm to very cool, right? For the same lamp. You have the glare index, which is 13.5, which is very close to 10. So we may consider this quite acceptable, right? It's very good luminary for general use. Then it is optimized. And this is important because it's LED, right? So they say, okay, optimized, I just become suspicious, right? But it's not certified or proof, just optimized. I see, well, we should check. We should have your engineer check in for that, right? Because, and this is among the most expensive in the market. Then we have the dimmability, and they follow both standards. So you can use all of them, right? So with this, just make in one word in your sheet, what is the CRI 92? What's the UGR 13.5? And how much can we expect about this optimized thing? Just a couple of minutes. You can speak, talk, discuss, fight, sing, look in internet, whatever. But just to review it and to become familiar with those terms. No much inspiration. CRI, what does CRI? What does it mean it's 92? That's good or it's bad? We just commented about it, right? Forgot already? This is like the fish memory thing. Okay. How is it going to those online? Because we have today just 15 people in class. Okay, so let's continue. There is more material in the lecture. I will not comment on it, just to have the data on different options to make artificial light in one room, right? Or the quality of different kinds of lights, generic, in terms of is a transformer, efficiency in watts, the lumens, and so on, right? This is an old chart. So we have mostly incandescent, analog, and fluorescent, and compact fluorescent. There's not LED here. This is a photo of the city where you can see clearly this white. Which kind of light is that in the main streets? That's the mercury, as we said, that's quality. That low quality in the alleys in the Palmo is the sodium light. Right. So there's plenty of standards for bulbs. So you have here some of the basic references for the standards. And this is a full chart for just fluorescent. Fluorescent has been so long in the market that we have a huge variety. Whereas LED is a bit more mysterious. It's more simple. This is for high intensity. Again, mercury, sodium. Halide is in the market, but I didn't see so often, right? So you know how they look. This is mostly for street or industry, airports, warehouses, and that. And LED, we don't have so many standard names. Right? It's a developing market. It's not totally normalized, but we already are familiar how they look. What is interesting is many of the lamps are designed in a way that they can fit the luminaries of fluorescent and incandescent, although they are LED, right? So let's go to the next chapter, mechanical, in just 20 minutes, which should be enough. This is a Kote Hospital, Uri Songu, kind of, it's a poetic vision of the industry. Mechanical systems can be beautiful. Well, it's not that it's my photo, but to say it. So HVAC stands for heating, ventilation, air conditioned, usually by air pipes or water pipes. And this is very ugly diagram, but it's still my diagram to say what is a full system for HVAC, cooling or heating, right? So you have the building, which we are conditioning. And for each floor or unit, we have like an impulsion and return of air, right? In this case, it is cool air because now it is getting warmer, and it goes through, it becomes warmer, and it's collected in what we call exhaust. Before that, we have like the supply element, right? The air handling unit, which is just a set of ventilators which push fresh air from the exterior. Actually, the fan is there. And either cool or heat it with the a kind of a spiral or a big exchanger of a hot or cold fluid, right? Which comes from either a boiler or a chiller, which is air conditioned. The air conditioned usually has two units. One which can be interior, is the condensing element, and the evaporator unit, which is usually in the roof or outside. This is the one which needs to be exterior, right? The boilers, if it's not electrical, will need some kind of exhaust for the smoke, right? Even gas, which is the cleanest, will need some kind of exhaust. So something you have to take into consideration. So with this, we have some elements which produce heat or cool. So that will make the air go through some filter and be pushed to the building. That's very basic principle. The exhaust is a bit more complex. In the old days, we would just throw it away, usually through the roof, so you don't disturb the street or neighbors or so on. That's as far as possible, so it diffuses in the atmosphere. When we try to save energy, especially after the 70s, 1% of that exhaust would be recycled with an addition of air from the outside, right? This is mixing a percentage of air. This is something we don't do anymore, right? Because the air you are collecting is full of dust, bacteria, microbes, smells. You want to put that again in the building. We have very high quality filters, so it could be filtered, but those filters need to be maintained, and so it's a weak point. So instead, what we do is the heat exchanger, which is a point in which the air is totally thrown away, right? But before going out, it exchanges the heat with the air coming in. So you change only heat. All the used dirty air goes to the atmosphere, and the atmosphere takes care of it. We don't care. We are eco-friendly, but we don't care about what we do in the atmosphere. We just put all our microbes there. And the air coming in just collects that energy, either heat or cool in summer, and comes fresh inside. So that's a very, very important point, which is becoming a standard in the recent 10, 15 years, right? Instead of just mixing air. I say that and spend some time here because in your assignments, I see very often you find somewhere all the tables and say, okay, mixing station of air, reuse air and fresh air. That's very old-fashioned way of doing. If you do that, you have to put a really high quality filter and preview for that, specify that and preview the maintenance of it, right? The gold standard now is the heat exchanger. They are very close to 100% in efficiency. So that's the basic. Then there are many ways to do it. I just collected the most basic diagrams, and these are very rough diagrams. When you make your assignment, don't copy this. Adapt this to your building, okay? So we have the chilling, the boiler, the chimney for the boiler, the cooling station, and then the air handling unit with the ventilator and exchange element, right? In this case, you see we have fresh air, exhaust air, and we have the mixing damper, right? There's something which I would question. I wouldn't use it anymore, although this is an edition of quite recent book. So here we would put the heat exchanger, right? This is the most simple constant air volume, the one we have in the school. Everybody gets the same air, cool or hot. You can regulate a volume, but in this case, we have no regulation. Everybody gets cool, everybody gets hot. Very simple, cheap, easy to maintain, but hardly efficient. In this building, we have sunshine in one side and shade on the other. Probably those guys will be happy and those guys will be freezing. So we are wasting energy. This happens in this building, okay? So to improve that, we have the variable volume. which is basically the same system, but you have a damper in each floor. So you cannot change the temperature, but you can change how much air you get inside. That's okay, because you can regulate what you have. It's more expensive if you have a lot of control elements and electronics there, much more efficient. The problem is if you depend on this air, on your ventilation, the air you breathe, you can never totally lock, right? So this kind of limitation of mixing two systems in one, just the air you need for breathing and the heating, cooling, but still better quality. Even more sophisticated is just the multi-zone. And this is a system which you have not only the air, but you can regulate the temperature, how much exchange you have. And the most sophisticated, you can even choose if having cool or hot, which in some times of the year you may have necessary, right? That means having boiler and chiller working at the same time. So it's not very efficient, but very high quality facilities like hotels also need to give the facility to use all of that, right? You have individual ducts, which means much more expensive, much more space, much more difficult to make. The other which we have in the school is the fan coils, right? So here ventilation and heating follow different paths. This is great because, again, we can have the boiler and the chiller working simultaneously. You can choose heat and cold. That's not the case here. Everybody gets cold or hot or nothing. And the air handling unit, that exchange happens in each of the fan coils, right? Fan coil is just a fan, right, which pushes the air, and the coil, which is the coil with the hot or the cold air, so that cools and heats. And this is what we have under the windows throughout the school. In that case, you may need to complement with mechanical ventilation. So you have the air inside. And just fan coil, in which ventilation depends on the facade, on the rooms themselves. They have not mechanical ventilation anymore, right? We have also just some basic dimensions for the window units. We try to avoid it because it's quite ugly and very inefficient, but sometimes we have it. And then once we choose the system, we have to decide where to put the air handling units and the machines, right? And there's like 4 options we have. Of course, this is very simple, but when you have your buildings, you have to really decide how to put it, especially those having a high-rise or very long buildings. You may need to divide in bits, right? So this kind of a floor-by-floor division is great for very much decentralized buildings, so you have a smaller space used there, right? In smaller buildings, you may have also that air handling unit anywhere. The only limitation is that you need to take the exhaust out and have clean air in. So that will need additional elements. This is why the roof is very common, because you have the best quality of air and the less disturbance to neighbors. But you will see almost anywhere. And well, this is for the cooling and heating units, the same, right? The easiest is to have everything on the roof. With a 1-floor building is very easy, but you will need always to have some exterior space. In the case of ventilation, you need only 1 duct to bring the air in. This is some tables for pre-dimensioning the units, right? So you know how much size you will need. This is very rough pre-dimensioning, but when you make the project, you need to know how much space you will need for those units and those rooms. And this is a basic layout of one room, one air handling unit. If it is centralized, it will be huge. If it is individualized, it will be smaller. The points, if you have contact with exterior, exhaust must be as far as possible from the fresh air. Otherwise, you will have contamination coming in, right? It should be as far apart as possible, or having just a duct going to the exterior, not just the facade. Then you need access so you can maintain the ducts and the ventilators. It's a huge box. You need a space on the borders for people just to make some basic maintenance and cleaning. That's additional element, right? And then you need big space for the supply duct to go to the rest of the floor of the building and for the return duct. So that means you will need to have enough ceiling space for those ducts, right? And enough space for them to go side by side. This is an example of a KT building in Guanghamon, Benzo Piano. And you see in this case, we have some space to the walls. That's what I said, we need some space to avoid sound transmission. The limbs are floating in a kind of elastic base. But there's always a space for some people to go inside to maintain and use the elements, right? In that room, you have a lot of many more things happening. It's not only ventilation, but this is the size of an air handling unit. You see the connections, filters, all those elements we saw in meet always in between. And this is an old building, new buildings, right? No matter how efficient the system is, about 75% of the roof is occupied by machines, right? In this case, yeah, almost 60%, or I think other systems, 50%. Still, you can play tennis in the roof. This is an interesting case. This is Detroit Medical Center. I know well this building because I lived there for a few months. This is 1980s, 1970s, 1978, I think. All the mechanical rooms are in the center, which is a good idea because you go up and down. It's very well centralized. You don't have big vertical ducts, but all the machines are here. So all the sound goes to the street and to the garden. So this street in front of the hospital is like being in an airport with airplanes near to detach, which is not great for a hospital space, right? And the same happens on the back, which is they have beautiful gardens and areas for resting and other buildings. You get all that noise day and night. So this was a bad idea. That's why we go always to the roof. Again, the core strategies we saw with the structures. Here you have some ideas for having more appropriate mechanical systems with the core, right? From very centralized, which is really office space, or a little bit more fragmented houses, hotels, which need like many shafts and more decentralized system, right? And this is a rating of different cores depending the possibilities for the MEP systems, not for the structure. And of course, in most towers, central is the one which gets the best scores in all cases, but it is not always the most appropriate. It depends very much on the layout of the floors, the use of the tower, and so on. This is very basic standards for you to choose. For example, KT building has all the cores just detached. So the main tower is totally free of use. Then once we have the section, we have to decide how those ducts are distributed to the floor. The basic standard is to have the main elements until this is the individual control. This is in which you can regulate the amount of air in one room or one unit. The main ducts should be in corridors or common spaces. Because if you have a problem in your office, you don't mind people to come to see your own controller, right? But there's something general happening there. You have to go to a private space, and there's always a source of conflict. So the common ducts better in common spaces. The same with the vertical shafts, right? In a rental building, it's a bit more flexible, but I see often those shafts and those conducts inside the rental space or private space. And that creates always a conflict of privacy, of rights, of maintenance, and invading and limiting the use of a private space when you need to have to make some kind of maintenance and use. So when you have your layout, think of this. And of course, the most common, as we said, is having the elements on the corridor to the rooms. This is how those kind of buildings happen. Right? The Changwing one follows this diagram. You can have the elements integrated on the floor. This is quite sophisticated. You need a lot of coordination, but very much many high technology buildings have this, so you don't have additional layer of ducts and things hanging around, right? You may have it decentralized on the suspended roof. Right? This is when you have one building belonging to one company and there's not kind of a private or common spaces. You have a lot of diffusion and you have very much distributed air. And you can have it to the floor, right? It's not very common, but many offices now have like individual control on the floors, so you can have the air in your desk. You can switch on and off and have the air you need without depending on the ceiling. One thing which is interesting here also, when you have the system, you have the impulsion and return. You have to design us here in a way in which the whole room will have the airflow, right? Sometimes we have examples in which we have a room. You have impulsion and return one next to the other, and that creates very, very poor ventilation. So ideally should be like impulsion and return in the other side of the room, right? Or at least separated reasonably so we consider the full room will have this kind of flow of air. And this is a standard example on how to put elements in the traditional buildings with a steel structure, right? So girder beams, so you need a lot of space for the structure. And then for the remaining, they say at least half a meter. If you go to any kind of Korean office, they will say you better give us 1 meter. That creates a lot of height, a lot of space between floors, right? The gold standard is to have ventilation, electricity, and water in the lower part. So any kind of leak will not affect electricity, right? And the ducts go first because they are the ones needing more space. If people put electricity and water, they will need to meet a lot of vents and so on, and it's not very efficient. That means the construction has to be very organized. Usually the MEP system, electricians, mechanical engineers, fire engineers, lighting, they all fight. Is kind of a battleground. Everybody wants more space. They want who comes first to first. So you need a lot of organization there. But usually is water below, right? And if you have toilets, as we saw in the hospital, that black water in the bottom, right? So it will never pollute or if had it leaks, it never interfere with the fresh water, and it will never have a problem with electricity within it. We have a first question. That detail was beautiful. You must like it. Well, that was a point here. Always electricity and water at least 5 centimeters, right? And we are 5 minutes from the end, which is great because we're almost finished. It will be finishing on time for the first time in many years, many days, many weeks. Okay, so those 5 centimeters between systems, gas is even more critical. We don't have usually gas inside, but you give at least 5 centimeters of separation between ducts, right? Well, I say that because year after year, in your assignments, I see the detail you make, whichever building, housing, offices, museum, just use the same detail. In some cases, adapted to have concrete, right? But in many cases, just literally the same lamp, the same luminary, the same position. If you make the detail, if you spend the time to sketch this in 20 minutes, 30 minutes, or 1 hour, think on your project, in the kind of luminary you like, the kind of structure you have, right? You should be thinking on your project, the space you create, not replicating the existing detail. because this is also design. This is part of your project. Okay. So final slides is just to tell that MEP is usually something mysterious. We send the project engineers, they bring it back and they just integrate in the project. But this is also part of the design. And this is a Seagram building. This one, this is the MEP system. That is very old-fashioned building, but it was reasonable. They have a full system near the windows. There's some kind of air curtain, which provides some kind of insulation between exterior and interior, right? And then a system of supply and return with individual units through the floor. Not as elegant as you would expect in Miss Van der Rohe, because it's hidden, but still kind of organized. This is as soon as Seagram was finished, the Chase Manhattan Plaza. It's like 3 years later. Gordon Bunshaft was one of the best architects in SOM ever. Right? He created a long, narrow building with a really quite beautiful layout, right? Concentration of the air in the borders and very quiet core space in which people do not stay. So it's really, the activity happens near the facade, and this is where all the systems are, right? It's quite clear, beautiful. Rescan, Chemoscan, okay, the medical labs. He had the real shafts, right? And then kind of actually curiously centralized system, but following as much as possible the idea of the building, right? Like a core and the different units together with a centralized point with more density. In this building, if you draw only the system, you have some kind of a familiarity, some kind of a consistency with the layout of the building itself. More radical is Kevin Roach, John Dinkerloh, some of the best architects of the mid-century in the States, right? In which the MEP systems kind of continuation of the structure and the full space conception of the building. Even better, I think Hertzberger, one of the Dutch structuralists, this is one of his most famous office building. It's about decentralized, atomized, right? Have individuality with plenty of natural light and open space inside. So even though this is very Dutch, they have a very much powerful central power station. The whole system follows this kind of, it's kind of a tree, right? Like little by little dissolving to the border, right? And this is a beautiful example of that. The extreme case of Norman Foster IBM, this is the democratic MEP. Everybody has his own individual outlet, and that demonstrates here. They have like plenty of small units to make like a really homogeneous democratic distribution. Very democratic, but I would choose to go near the windows. I would never try to work in the central area. That's another thing. More examples, Google, and well, yeah, we're on time. Messy building has a messy system. That's consistent in some way. And then the most democratic is the Bank of America, in which each has its own air outlet. Curiously, people are calling me by phone from, this was from Spain. Now it's night time, so I don't know who's calling. This was one system in which each worker has individual air outlet with individual control. It was like the gold standard. We're speaking of 2009. It's quite recent technology. Curiously, it has been one of the most inefficient buildings in terms of energy. That means that individual regulation does not solve anything. Demonstrates people are totally careless about energy and they will just use it randomly. So it's not a good idea. Sounds well in theory, but it didn't work here. Here's some photos, Katy Tower. I will not comment much, just telling you the consistency. Mechanical goes first, it's the most difficult. But even those 50 centimeters are very tight. And you will have very difficult points when you have to cross elements. Every time you have a kind of bending, you lose energy and you make noise. Right? This is very high quality building. They have low speed. Low speed means larger ducts, but very pleasant environment because you don't feel you don't have noise, right? This is the conflict, right? Even with the structure. And you see the fire protection is broken. So in case of fire, this will be a weak point. Very careful with those guys. And then this is very high quality. Very much many outlets with the very long diffusers. So you will not feel the air moving, not even the sound, because you have a big volume with very small speed. And this is how it ends, right? So instead of those outlets we have, which are concentrated, long elements are much more, will give a less speed of air and less noise. In this KU hospital, just to see the contrast, in this case, it is individual units, but you see this is just for ventilation. This is another system which is totally packed, right, for probably insulation and safety. I never saw so much carefully packed systems, but probably this is because the hospital use. And then the hot and air, the units, the cassettes, just recycle the air inside. That's the fan coil system, but a bit more sophisticated. This is the shafts. You see the condition elements, the top and the bottom. And again, some control box, not yet finished, and some space for the operators to work inside. Those areas should be fireproof, right? And often they have cutting devices between floors, so the fire will not go in vertical. This is one of the weak points in case of fire. You see here how big those ducts come. This is kind of intermediate floor for installations, for machines. And this is terrible because, again, it's noisy and lose energy, but you need a space for people to walk in. All the ventilation pipes hanging. And what we saw the other day, or yesterday actually, the ceiling for noise, safety, fire, and all those things, right? So this kind of crossing between sectors in the building is something which must be carefully done, right? And you see always electricity in the top, water below, right? And again, this is something you try to make as little as possible. Probably the following floors are a bit different. I have to change the vertical. All those elements will create a noise and energy loss, but still it's quite reasonably done. The complication of hospital is something which you won't see anywhere else. Yeah. If you compare with the office before, KT is so different, right? So you have all the pipes, huge ducts which come from the basement. And our guide said, well, in hospitals, you need a lot of air handling and a lot of space for those shafts. And then just two tables for you have the instructions there. You have the dimensioning of the heating, cooling equipment and the air handling unit, again, for pre-dimensioning the project. And this is the summary for HIVAC. So you have to choose the system, as we said, organize or find the space for the machine rooms and the shafts, then the layout of ducts in plans and sections, and then pre-dimensional. Those elements need a lot of space. You need to know the dimensions because that will change your project quite fast, right? And then in the end, how they relate to other systems. As we said, we need to share the space. And that's it. We are finished. 6 minutes over. You can complain if you want, but we finished the lecture. So that's it. I have all the assignment 2.1 offline corrected. Still, Kanunjin didn't come right. It's over there. I returned them. Those online will be posted probably this weekend. Okay, so usually It's not through discrimination, but I review first paper and then go to the computer. It's a bit longer. Don't forget next week to submit the assignment 2 and have a nice weekend and a beautiful Friday 13th. See you Thursday.